understand that I present myself. So my name is Naftali Tishby. I'm a professor at Hebrew University. I've been working on machine learning before it was called machine learning since the 80s. I want to tell you about, so I'm sure you all know about deep learning. And if you really look at the history of artificial intelligence, it can easily be divided into three phases. I mean, the first phase between the 50s and 80s, which we usually call the logic phase, where AI was essentially based on lookup tables and rule-based systems. And to some extent, some people are still doing it, but this never really worked on large and interesting problems. The second phase that started in the 80s is the phase of machine learning, which essentially it moves from logic to statistics. And using statistics, or what we now call statistical learning theory, or statistical learning, or machine learning in general, instead of dictating the rules to the systems, we actually let the system learn by themselves from data, from examples. And that's, of course, one of the main reasons we're all here. And to some extent, this phase between the mid-80s and the late 2000s was really characterized by what we now call curve fitting, essentially a very old idea, which is due to Gauss, actually, and just fitting functions to data in a way that regularized the complexity of the function. So we control what we call overfitting. The last phase, which we now clearly see is a new, different phase of AI, is what we call the deep learning phase, where we went back to actually a very old idea, which started already in the 40s of the last century, which is really stacking together neuron-like elements, or essentially linear threshold functions with some sort of nonlinearity. I'm sure most of you know what it is, in many, many layers. And those functions, those deep neural networks, as we call them today, or the deep layered networks, essentially change the rules of the games in a very dramatic ways. I mean, essentially, many of the dreams of AI, which were really just science fiction until more or less then, I mean, the mid-2000s, the late 90s, and suddenly became true, whether we talk about vision, computer vision, image recognition, whether we talk about speech recognition, whether we talk about language understanding, and so on, as you all know, I'm sure. So, but deep learning, one of the big things that happened between the 80s of the last century and the 2000s is really a significant growth in the scale of the problem. I mean, it went from, let's say, pixels of an image of a few hundred pixels to megapixels or many megapixels, which is really a 4 orders of magnitude growth in scale. And that's really the main difference between the old machine learning and the new or large-scale machine learning. And one of the reasons, deep learning is, of course, a very big news for anybody who's using AI, but it's a very big headache to theoreticians because we don't really understand how it works so well, or why it works so well. And that's really a fundamental problem because we cannot provide any theoretical guarantees for performance. I'm sure many of you know about adversarial examples for AI. I mean, we can actually trick the networks to misclassify by very small changes which are imperceptible to human eyes. And this is really a very big problem. Like, we can't trust it in autonomous driving or in surgical devices or many other applications of AI today, unless we really understand what's going on. So my work in the past 30 years, actually, but mainly in the last 5 years, is focused on trying to understand why machine learning works so well and to provide some sort of theoretical guarantees to its performance. So I'm going just to go very quickly through some very complicated type of theory, but just to let you know that we're actually not in the dark anymore. We really begin to understand what's going on there. So if you think about deep learning as a cascade, let's say, called the input variable, like the pixels of an image, let's call it X, and the label, I mean, is it me in the picture or not? Let's call it Y, just for simplicity. Essentially what deep neural network is doing is transforming the input through a cascade of layers, layer by layer, which essentially changes the representation from layer to layer, and eventually the last layer, after many layers, is able to generate a prediction of the desired label Y, but it's not really Y, it's a prediction of Y, so I call it Y hat. So this is essentially all the notations I want now. And the way I think about it, and again, I'm making a very long story very short, is just a cascade of filters. imagine that each layer is filtering out some of the features of the input in a way that eventually the last layer is able to make very easy predictions because it remembers only what it has to remember and nothing else. So the way we think about it is really as some sort of a cascade of tubes, if you want. I mean, leaky tubes. Each layer is allowing only a fraction of the flow of information in the layer to go on, and this flow of information is actually enhancing the signal to noise or the clarity of the message about the label, and that's why they work so well. So you can think about it also as a cascade of nonlinear filters that really filter some frequencies or filter some features of the irrelevant representation of the data. And the question is, how does it work? So one of my main ideas that has been leading to a lot of new insights is that essentially it's enough to look at the layers in only 2 dimensions. The information that each layer has about the input, the mutual information in the sense of information theoretic Shannon mutual information, and the mutual information that the same layer has about the output. So remember these 2 axes, the information about input, information about output, and that's essentially all we need to remember in order to understand how it lands. And if I actually look at the learning process in this plan, I see a very interesting question. Different networks initialize differently, have different training data. As long as they have the same architecture, they have a very similar behavior, very similar trajectories in this plan, which we can really summarize by this type of picture. Essentially, all the layers move first up and a little bit to the right, which means that they remember more about the input and more about the label, which means that they generalize better. So that information about the label is telling me essentially how well I generalize. But there's an interesting phase, which from A to C, they move very quickly and up. And then from C to E, the last layer is actually moving up, but to the left, which means forgetting information about the input layer. Essentially, this is precisely this filtering, but this happens in the second phase of the learning, which is really where the training errors seem to move very little. And the interesting story that we can explain exactly why it happens essentially due to these 2 phases of the gradient descent that we are using, the stochastic gradient descent, the noisy gradient that we feed the gradient of the error that we feed the network. And essentially, the first phase is what I call memorizing the features. This is essentially just fitting the data, or empirical risk minimization, if you want. But the second phase, which is really much more important for generalization, is this slow compression of the input features. And the interesting story is that if you actually look at those traces, so this is the same picture, just the color here represents the number of iterations on the number of epochs of training. You see that if I have enough data, this second phase is actually putting me into this interesting point where the last layer really remembers only, in this case, 1 bit about the input, or only the minimal necessary information to make a prediction. This is what in statistics is sometimes called minimal sufficient statistic. So essentially, the layer by layer, really pushed the last layer to this point of remembering only the minimal necessary features of the input in a very efficient way. If you don't have enough data, by the way, the first phase looks very similar. I mean, fitting the data is actually very easy, even with very few labels. But the second phase is inefficient, and you end up in a very poor generalization. And that's precisely where things like early stopping or don't overfit work better when you don't have enough data. So you really see how this picture changes with the size of the data. A lot of data, this compression phase improves generalization and improves the representation of the last layer. And when you don't have enough data, this compression phase is actually hurting you. But what I want to tell you today is it's not only we understand exactly why it happens, we also understand what is this line that you see that the layers converge to. And this line, which I call the information bottleneck bound for reasons which I don't have time to explain here, essentially the optimal trade-off between compression and prediction of generalization. And this can be calculated from the problem alone. It's not a property of the network. So that's a very interesting consequence. I mean, essentially the layers converge to something which is independent of the architecture. It depends only on the problem. And the different layers you see here, those yellow spots, essentially, the different layers converge to different locations on this optimal line. And one of the interesting consequences, which is completely surprising to a lot of people, is that, let me skip some theoretical slides here, is that essentially the time that it takes to converge to a good solution in terms of iterations, number of epochs of training or number of updates of the weights. You know, we actually run it through a lot of data many times. That's the whole story here. So there's a long dynamics of thousands and thousands of updates of the weights. So if you actually calculate how long does it take for the network to converge to a good solution as a function of the number of the layers. So the intuition is that if I add more layers, I have a more complicated model, and therefore it probably take longer time to converge. This is the common wisdom in the area. What we are seeing here, and what I am going to actually argue that we understand mathematically, is that the opposite is true. More layers converge faster. And this is really one of the biggest secrets of deep learning. I actually converge significantly faster when I add layers up to some point when the layers become degenerate. So as long as they're able to divide this area in the information plane, and each layer is actually compressing different part of information. So more or less, they divide the irrelevant components of the data. Let's say if it's an image, what is the background, what is the illumination, what is, if I have a hat or I have glasses, I mean, all those things which are irrelevant or nuisance variables, which are actually the most important, the hardest part of the learning is really to identify those and to get rid of those. This is unlabeled, by the way, it's completely unsupervised. So it's actually very weakly supervised. But what we see here is that we add layers to the network, and the network actually converges much faster to a better solution. And what I want to tell you now that you actually understand the theory behind it, which has to do with the way this compression happens. And it happens due to the noise in the gradients. And essentially what I'm saying is that the noise in the gradient is filtering by reducing the signal-to-noise ratio of the irrelevant variables more and more layer by layer. And when I just do a very simple calculation here, you get essentially this very surprising result that when you add more layers, the number of iterations to converge to good generalization goes down in a log-log scale. That's what you see here. So it's the log number of layers versus the log of the number of iteration. You see a straight line. This is what we call a power law, which means that the time to converge to a good solution is some power of the number of layers. And this power is actually predictable from the theory. It should be around -2. It's a negative power, which means that it goes down with the number of layers. And 2 is the expected prediction. So it's a quadratic increase of time if what happens is essentially just independent diffusion in each one of the layers, independent random walks of the weights in each one of those layers. So what we had is this, the orange line here is the prediction of the theory. And then we looked at some of our networks. It changed from problem to problem a little bit. But what we saw is this blue line, which was almost a perfect fit to the theoretical prediction. And actually, we see it in many other problems. This is the toy problem, but here we see the same thing at MNIST, and we see the same thing at CIFAR, and we see it with ReLUs, and we see it with convolutions, and we see it essentially with many, many different types of architecture. We see different types of power laws, but as long as you have more or less fully connected networks with essentially unconstrained architecture, you're going to get this enhancement of time with the number of layers. And that's just one particular example of what I call understanding the theory. I mean, if we have it, we suddenly understand that the layer is actually doing something which is much more than just expressive, more complicated functions. It's actually enhancing the dynamics and the time to convergence. For big problems, this is a very big boost. But there is another thing. I don't know, I have a lot of time. Okay, so the main new development in this theory, which I call the information theory of learning, is where do these layers converge to? Again, if you look at those plots that I showed you before, there's something very striking. Look at those yellow spots that I mentioned before. This is where each one of those layers end up at the end of training. And you see that only the last layer goes to a very good generalization. The other layer gets stuck in some places along this line, which means that they actually represent different features. They don't forget everything, but each one of them is forgetting something that the previous layer knew and is giving me some sort of, so each one is really responsible for filtering some particular features. And that's very interesting. So if there's a hierarchy of features, let's say you do face recognition. So of course, to first approximation, my head is just a sphere, you know. And then to second approximation, there are maybe some hair up here and some, who knows, two eyes, and essentially there's this left-right symmetry, more or less, and so on. Actually, when you add more and more details, more and more features become important. And of course, there are more and more features to ignore. For example, I don't care about my background, and I don't care if I am illuminated from above or from below, and so on and so forth. So the point is that each one of those layers is actually able to capture some of those features and eliminate them. So the interesting question is, can we actually interpret, can we actually say what each layer is filtering out? This will be close to what I promised in the title, something which is an interpretable deep learning. If I could actually tell you, look, the first layer is responsible to these features, second layer is to some finer features, and so on, or maybe coarser features. And only the last layer is doing some very coarse two-clustered generalization, and actually I can tell you which one is responsible for what. This will come very close to interpretable neural networks. And that's really our goal. And the surprise is that there's actually a good theory behind it. So if you actually look, and this is going to be slightly stretching your patience, but just a little bit. If you actually look at this information plan, the x-axis here is, again, information about the input. Remember how much the layer really compressed the representation? And the y-axis is essentially what type of features or what type of representation I have at this level of compression. And this is, by the way, the whole diagram, the whole tree of splits here that you see. This is what we call a bifurcation diagram of the representation. Essentially, at each split here where you see that the point is split into two, a new feature appears in the problem and is actually telling me, at this point, these features become important. And so this particular plots, I mean, the number of features, the number of classes that are distinguished by a certain layer at a given level of compression, or the whole tree of bifurcation, is completely determined by the problem, not by the architecture. So you give me the problem. I mean, for example, you do face recognition, you do speech recognition, you do some sort of NLP, whatever. You give me the input and the output statistics, even just approximately, and this is based on just a sample of 5% of the data. Just a sample of your joint distribution, which is essentially what you have in order to train your data, your network. This is why we need big data. This can be a huge sample, but just by a very simple, in principle, computational procedure, I can calculate this tree of bifurcations or splits. And now I can tell you, look at this plan where each layer stops, and I'll tell you what does it represent. By essentially looking where is it, for example, if it's along this line here, I can tell you, and let's say there's one layer here and one layer here, I can tell you that the difference between these layers is the merging of all the splits in between. So essentially, this layer doesn't see the resolution that this layer is seeing, and this particular split is exactly what was merged or unified between these two layers. So essentially, this is a very concrete prediction. Look at the information plan representation of your layers, and I'll tell you exactly by looking at those splits, and I can look at them in great detail. Each split is associated by merging some features. So for example, if you do NLP, they can be properties of words, like big objects or small objects. So you can talk about big furnitures and small furnitures, or big animals and small animals. And what we see in this type of analysis, that the notion of small or big, this dimension of size, is actually appear at one place in this representation, and it happens to all those things together. So furniture split by size, animals split by size, and so on. And we can actually identify, so this particular layer is going to be sensitive to the size, and the layer after this is not going to be sensitive to the size anymore in terms of its new features. So essentially, we can decode the structure of the layers just by looking at this type of diagrams. Okay, so again, the theory is somewhat more complicated, but the fact that we can actually do this, at least very simple problems, and really tell you this particular layer is responsible for these particular features, and actually it's a prediction on the weights. The weights can be completely random, but there's something like the singular value decomposition of the weights or some spectral decomposition of them can actually tell you exactly what type of questions about the data is answered by each one of the layers. Okay, so this is great news for us. Of course, it's not yet done on industrial scale in the sense that if you really give me one of your own practical problems, a very large problem, let's say in NLP or in vision or whatever, it's going to be very difficult to generate this type of diagram. But in principle, it can be done. It can be done for simple, relatively simple problems in object recognition, let's say distinguish between cats and dogs, or distinguish between humans and non-humans, or things like this, which are important. We can actually do this type of analysis and then come to the network, and it can tell you exactly what each layer represents. So very surprisingly, I actually got to the end of my talk on time. So I just want to summarize. So essentially, the first quite surprising message is that only two numbers, information about the input and information about the output, which is a huge reduction in complexity. I moved from millions of weights to only two numbers, tell you the whole interesting story about the dynamics of the training, how long does it take, and about the trade-off between sample size and accuracy, which is really the main question in learning. How many examples you need in order to achieve a certain accuracy, or the opposite, given a certain accuracy, what can you do with your given data? So in principle, everything is described by these two numbers, and these two numbers tend to concentrate. The larger my problem, the sharper this picture in this information plan. That's the main message. And then I'm actually saying that most of the learning is actually going to what I call forgetting irrelevant details. Most of the effort of the training is this diffusion process, which allows me to ignore the irrelevant. So actually, I'm saying that the important part of learning is actually forgetting. And that deep learning is actually doing much more than curve fitting. Curve fitting, which is the old machine learning, was essentially just regularizing somehow the functions that they will not overfit, but otherwise it's just fitting points to data in high dimension. Here there's a new feature, which is this elimination of the irrelevance in a systematic way that is done by the SGD. And the second message I gave you is that the advantage, or the main advantage of many layers, is not in the expressivity, meaning expressing more complicated functions, but in the time to converge. And more layers converge faster, and in large scale, it's very, very important. You actually find a good solution faster. And of course, there are many other things that I just hinted on. You can actually interpret the meaning of the layers in some very special problems, and you can actually, in principle, decode or break this, open this black boxes if you want, or actually tell you what each layer is learning. And there are many, many other things that I'll stop here. Thank you very much. There are no questions, no? No time for questions, is there? Yes, one question, okay. Automize it. Yes, okay, very good question. So I mentioned here at the end what I call design principles. And design principles are, you don't see it. Design principles are precisely this what I can, given the problem, what is the best layer, the best network for this problem. And what we actually say, that if I have the problem and I have enough statistics of the data, even without training any network, I can tell you how many layers are going to be most effective here. And essentially, it's both the number of layers, the size of the layers, which actually is less important beyond a certain size,
And I actually argue that the other details, whether you use ReLUs or sigmoids or whether you use convolutions are very important because they allow us to reduce the sample size dramatically by essentially embedding symmetries into the problem and invariance properties of also. That's why convolution is so successful. But in principle, we are going in that direction exactly. I'm able to give you more and more design principles and engineering principles, and maybe the more important, some theoretical guarantees to avoid the problem of adversarial attacks and so on. I see that I'm out of time, so I'll stop here. Thank you very much.